So, having discussed electrons Green's function elaborately, let us just touch upon the Phonon Green's function, and before that let us emphasize the importance of Green's function for a moment. So, the Green's function, the pole of the Green's function rather, gives the excitation energies of the fully interacting system. We have started looking at different orders of the Green's function, that is whether the Green's function contains one interaction term or two or three and so on, and it turns out that they are quite complicated. Because a third order Green's function would necessitate calculation of over 5,000 diagrams without taking into account the symmetry requirements. But nevertheless, Green's functions are very useful because the poles give the excitation energies, and we will also see that even a fully interacting Green's function, that is taking into account all orders of interaction, it can be solved exactly, and the form is not too complicated, and this is done by using Dyson's equation, which is what we will learn. But before that, let us review a little bit on the Phonon Green's function. However, most of our discussion will stick to the electrons Green's function. So, the Phonon Green's function is written as let us write it with a d, and q is the momentum. We will write lambda and its t minus t prime has the same form as we have seen for the fully interacting Green's function, and it is a time ordered product of a q lambda t and a minus q lambda t. These capital A's are combination of the bosonic operators or the operators for phonons, we will see in a moment. Now, q is of course the momentum that we have seen earlier, and lambda is a polarization. Most of the cases the interactions that we consider for the phonon system, they do not mix polarization. So, it is safe to get rid of this polarization index lambda, and the a q's without the polarization index are written as a q plus a minus q dagger, and or equivalently one can write it as a q equal to a q. So, this is say involving the lambda, and then we can sort of remove the lambda as well and can write it with. So, we will remove lambda in this step and write it without that, and these are the combinations. So, a q operators are combinations of a q's and a minus q dagger. So, the full phonon propagator in the interaction representation is written as d q, or we can write it inside as we have written above. So, q t minus t prime equal to a minus I, a time ordered of a q t a minus q t prime, and the S matrix and this is S matrix in the denominator. So, this is the full Phonon Green's function, very similar to the electron Green's function that we have seen, including the S matrices which were written earlier. So, if you open up the AQs, the capital AQs in terms of the small AQs, one can write down the Green's function, or let us write down the non-interacting phonon propagator without the S matrices. So, this is equal to d 0 q t minus t prime equal to minus I t a q t a minus q t prime, it is equal to minus I t. So, there is a aq exponential minus I omega q t. So, that is the time dependence of these operators, plus a of minus q dagger exponential I omega q t, and a of minus q exponential minus omega q t prime, and plus a q dagger exponential I omega q t prime. And so, understanding that the angular brackets are for the non-interacting ground state, so at 0 temperature it is known about phonons or bosons that AQ dagger is equal to 1, whereas the AQ dagger AQ is equal to 0. So, combining these information, the 0th order Green's function for phonons is written as minus I, and a theta function t minus t prime exponential minus omega q t minus t prime plus a theta t prime minus t exponential I omega q t minus t prime. And this is the form for the 0th order Green's function for phonons. And now the Fourier transform is given by d 0 q omega, which is equal to a minus infinity to plus infinity dt exponential I omega t d 0 q t. And if we do that, then this will be omega minus omega q plus I eta, and so this integral will yield omega plus omega q minus I eta, where eta is greater than 0 and infinitesimally small. So, what I did is that I have just put this d 0 q t from the line above or the step above, and then did that integration. Infinitesimal. All right. So, this is the form for the 0th order Green's function, and if you simplify it, it looks like q omega, it is equal to 2 omega q and omega square minus omega q square plus I eta. So, this is the non-interacting Phonon Green's function. So, at finite temperatures what happens is that these expectations have values that are that involve the number operator for a given q, which is this is equal to n q plus 1 and this is equal to the number operator n q, which is given as the Bose distribution function given by this. So, the total the Green's function above is given by at finite temperature. So, it is d 0 q t minus t prime equal to minus I, putting it in d 0. So, this and then there is a n q plus 1 exponential minus I omega q and there is a mod of t minus t prime plus a n q exponential I omega q at t minus t prime, and that is the 0th order propagator for phonons, and then one can do a Fourier transform and write it in omega q omega space. Let us take a typical electron phonon interaction. We shall not consider a phonon phonon interaction because phonons are the quasi particles. So, it is assumed that the quasi particles are non interacting. So, electrons can interact with phonons and electrons of course can interact with electrons. Here we will only consider electron phonon interaction. So, interaction is of the form sum over q k sigma. There is a vertex or a strength of the interaction which is m q and it is a q and c k plus q sigma dagger c k sigma. So, there are two fermion operators, one creation, one annihilation, and along with that the phonon operator which is a q, and m q is the strength of the interaction. Now, something interesting can be noticed here. That this term is equal to 0 because each a q contains a q and a minus q dagger kind of operators, and the ground state expectation of each one of the terms a q or a q dagger is bound to be equal to 0. Because if you create a boson in the ground state, then you have one boson more which will have 0 overlap with the original ground state, and same with the other term which is a q. Thus, the terms involving linear powers of a q, capital A q, would all be present, and not only that, all the terms with odd powers of a q will all be absent. So, it is only even powers of a q which will be present, and one can write down a linear in terms of quadratic. So, quadratic in V is what survives, and a quadratic term in V is then the full Green's function can be written as t minus t prime, and it will be g 0 k t minus t prime and plus minus I cube divided by 2 minus infinity to plus infinity dt 1 and minus infinity to plus infinity dt 2. And now I have a sum, there is a q 1 and q 2, each one will have a vertex m q 1 and m q 2, and now I will have the phonon operators and a q 2 t 2 and sum over k 1 k 2 sigma sigma prime is equal to t and c k sigma dagger t c k 1 q plus q dagger sigma k 1 plus q sigma t 1 and c k 1 sigma t 1 c k 2 plus q dagger sigma t 2 and c k 2 sigma star t 2, and so there are these. So, one creation with sigma, the other could be this is sigma prime, and then there is a c k sigma coming from the definition of the Green's function for electrons is this. So, these are the terms that are that will be present, and now in order to write down the electron part as the non-interacting Green's functions, we have studied how it looks like. We just worry about the phonon propagator at the moment. So, that gives me easily T A q 1 T 1 A q 2 T 2 I delta q 1 plus q 2 d 0 q 1 T 1 minus T 2. So, that is the let me write it neatly. So, that is so delta q 1 plus q 2 will be equal to 0, which means q 1 equal to minus q 2 and that will be with I, and then we have to compute the non-interacting phonon Green's function, which is what we have learned how to calculate it here. So, that will be the energies square. So, the electron Green's function of course has many contributions, and there will be since there are 5 rather there are 3 Green's 3 electron 3 creation operators and 3 annihilation operators for the electrons. There will be 3 factorial combinations which would allow us to write down them down in terms of the non-interacting Green's function for the electrons. So, which we have learned. Now, let us discuss more on the. So, we will stop with the phonon Green's function here and discuss with continue discussing with the electron Green's function. And so, there are some things about the electron Green's function which we have seen shortly or rather briefly, but we have not discussed them in great detail. So, let us discuss them, the ones that we have started. So, coming back to the electron Green's functions. Yesterday or in the previous discussion, you might have seen that we had diagrams of this kind. So, this is a q equal to 0 and there is a k, and then we had written it with time, but if we Fourier transform, we will get an omega here, we will get an omega here, and this is some k 1 or k 2 depends on which of the diagrams you are calculating, and this will correspond to energy k 1 and so on. And so, this is q equal to 0 and omega equal to 0, it is an instantaneous interaction. And similarly, there is another term that we had considered earlier, that is this one, in which there is a k omega, there is a k minus q omega minus omega, and there is a q omega that is been carried by the vertex, and then finally, the free electron Green's function is given by this. So, what happens is that at this point, let us call this as A. At this point, there is a vertex or there is a wiggly line which has a strength V q and has an energy dependence which goes as omega. So, that takes away some momentum and energy. So, the electron is left with k minus q and omega minus omega. Finally, they reunite here at the point B and continues as k and omega. So, these two classes of diagrams is what we had seen. So, this is, let us call this as A and this as B, and see that what can they tell us and how we actually use them to calculate something that is of importance to us. So, A is known as the Hartree term, and the B is known as the Fock term. So, we shall see that the Hartree term gives 0 contribution for the Coulomb interaction. And since we are discussing the first order perturbation, there is no change in the wave function. We only get renormalized energies, and the first order correction is computed as the expectation value of the interaction Hamiltonian between the ground states. So, correction to the unperturbed energies is obtained by a psi h prime and a psi, and in this case we know that this h prime would have to be between the non-interacting states. So, the underlying assumption is that in presence of the perturbation, the system has not gotten too far away from the ground states. So, the ground states are still good states for the problem, and we simply want to calculate the change in energy and for the interaction term to be squeezed between the non-interacting ground states. And this can be written as it is equal to half and will be k 1, k 2, q. Now, q should not be equal to 0, and sigma and sigma prime with a V q will just come in a moment y q is not equal to 0, and then I have a phi 0, and then I need some space here. So, I will just write it C k 1 sigma dagger C k 2 sigma prime dagger. Let us write it a little lower than that, because I need some space upstairs. So, and then we have to write the phi's also. So, phi 0, I mean they are in the same. So, let me, so there is a V q, and then there is a C k 1 sigma dagger C k 2 sigma prime dagger C k 2 plus q sigma prime and C k 1 minus q sigma, and this has to be taken with the phi 0. If you look at the Coulomb term that we had written earlier, this is exactly the form that we had taken. And what is our V q? V q equal to 4 pi e square by q square, and this blows up at q equal to 0. So, q equal to 0 term from the summation will have to be dropped. And now, look at the pairings, we will write down the pairing. So, if we can take a pairing between this and this and this and this, both correspond to q equal to 0. And we can also take pairing between the first and the third one and the second and the fourth one, both will correspond to delta k 1 is k 2 plus q, and of course, also delta sigma sigma prime. Now, you see that the Hartree term corresponds to q equal to 0, which is not included here at all. Any of the two terms any of the pairing comes from these pairing these lined terms, the terms that are being connected by the horizontal lines, they are not included. So, Hartree terms, Hartree diagrams, they do not contribute for the Coulomb interaction term. So, this is one nice information which see every information in this regard is useful, because we had to calculate a large number of diagrams. So, we are trying to reduce by using symmetries as much as possible. So, Hartree term. Now, there are two such terms, if you remember, one with a k 1 and the other with a k 2, and both will not contribute. So, Hartree terms do not contribute for Coulomb interaction. So, this is something that is interesting and important. So, we will just put a line here. Now, let us look at the Fock term. And the Fock term is simply, so this lower one is the Fock. So, this is the Hartree and this is the Fock. So, this term looks like, so this demands that k 1 is equal to k 2 plus q. Remember, all these k's are vectors, they are wave vectors, but we are writing it without the vector notation. You can put them, but it becomes somewhat messy to write every time with vector, but understand they are vectors, and this also demand that sigma equal to sigma prime. So, there is also a fermion loop that brings a negative sign. So, my H prime simply becomes equal to k sigma C k sigma dagger C k sigma and half, then there is a V q, q not equal to 0, and then there is a C k plus q sigma dagger C k plus q sigma, and that is the combination. Now, if we call this as a minus Hartree Fock energy, so including the Hartree, because Hartree does not give any contribution, then we can write down this term as a k sigma, and there is a Hartree Fock and energy of the Hartree Fock, and then C k sigma C k sigma. So, the expectation value of H prime between the non-interacting ground states is equal to some epsilon H f, which is the Hartree Fock energy given by this term, which is the sum over, there is a half factor as well, sum over q not equal to 0 or V q, and then this expectation value. So, thus the total Hamiltonian including this energy correction at the Hartree Fock level is equal to, so this is including, so this is just the, okay, let us just write the Hamiltonian, which will are only writing the interaction term. So, this is, so interaction, we can put an interaction Hamiltonian. So, that was not the total Hamiltonian. So, this is equal to epsilon H f and C k sigma dagger C k sigma. So, that is those are the two single particle operators, and there is a sum over k and sigma. Now, simply we can write it as epsilon k C k sigma dagger C k sigma, that is the Hamiltonian. Now, if this Hamiltonian has some other terms which are at the 0th level, then that has to be added to this term and so on. So, let us look at the Fock term more carefully. So, this is equal to I. Now, I will do the Fourier transform and go over to the omega space. This 2 pi in the denominator is routinely put for the normalization, and then there is a half, and then there is a q v q, and there is a g 0 and a k minus q omega minus omega, and then there are g 0 square and there is a k omega. That is like saying, if you go to this, there are two g zeros with k omega on the left side and the right side of the vertex, and then there is one g which is here, and then the v, there is a v q omega, that v. We have written v q, but it is also a function of omega. We will see that how that goes. Now, let us call this thing, entire thing here up to this, to be something called, because we are summing over q, and we are, so let us call this as sigma omega. We are summing over q and we are also summing over capital omega. So, this is equal to a sigma of omega. So, this is what we get from the Hartree Fock term, where we are writing one of the terms is equal to the part of the Hartree Fock term to be equal to sigma of omega. Now, look at n equal to 2, a typical n equal to 2 diagram. So, there is a k omega, there is a k 1 minus q 1 omega minus omega 1, there is again k omega, there is now k minus, so this could be just k minus q 2 omega minus omega 2, and then there is a k omega, and this carries, this one carries a q 1 omega 1, and there is a q 2 omega 2. So, this one can be simply written down as G 0, write it k omega sigma k omega G 0 k omega sigma k omega, and because we are summing over that internal energies which are capital omega 1, capital omega 2, etc., and this and so on. Sigma omega is defined above. So, sigma can actually be a function of, it is actually a function of both k and omega, because you are summing over q. So, it is a k omega. This is called as sigma k omega, is called as the free energy. And let me, this is an important thing. So, let me box it in red color. So, this is called as a free energy. So, diagrammatically a second order term is written as this, and then there is a sigma, then it is this, and there is a sigma, and then it is this, and so on. So, at the second order we have 2 such sigmas, and in the third order there will be 3 such sigmas, and if we consider an infinite series, then series we can write down a full Green's function. Let us write it with a double arrow, which is equal to a single, let's take it to the new page, because this is going to be used. So, full Green's function is written with a double arrow, double line with an arrow, and the non-interacting or the unperturbed one is written with a, so this is a g k omega, so this is g 0 k omega. Now, I will have a line and a sigma and a g, so this is a g 0 sigma g 0. I am dropping all these dependencies. So, this plus, and then there is a plus sigma sigma. So, there is a G 0 sigma G 0 and sigma G 0 and so on, and going up to infinite order, one can write down a GP series with a G 0 k omega, and then there is a sum over n equal to 0 to infinity, and then there is a G 0 k omega sigma k omega and n, and this is equal to G 0 k omega 1 minus G 0 k omega sigma k omega. It is equal to 1 divided by G 0 inverse k omega minus sigma k omega. So, this is called as Dyson's equation. It is called as Dyson's equation. This is what we were saying earlier, that we could do a perturbation theory with up to first order or up to second order or up to third order. Now, in some given problems, a perturbation theory can fall insufficient up to a particular order or a given order, in which case one has to actually sum over infinite number of terms containing infinite number of h primes. Now, formally that may look somewhat difficult, because we know that after, so we go from first order, we have first order we had 6 terms, second order we had 20 terms or something like that. If I remember it correctly, there are so second order, so from the 0th order it goes up to, so 0th order there is 1 term, first order there are 6 terms, second order there are 120 terms, and third order there are 5040 terms. So, this is the magnitude of the problem that we otherwise need to find out, but here up to infinite order, which is taking into account repeated interactions infinite number of times, one arrives at an expression for the Green's function, which looks very simple, with a G 0 and a self energy to be computed, and we have given the form of the self energy, and this one is with a G 0, as we already know that this is equal to a non-interacting Green's function, which is psi k plus I eta k being the sine of psi k. And in which case our full Green's function looks like minus sigma k omega plus I eta and I eta k, and so sigma is equal to a term like this plus a term like all these and so on. And so on. So, consequences of Dyson's equation. So, this is the first one of them is that far less actually a number of diagrams to calculate. And second is of course, the interacting Green's function. Full means interacting Green's function. Function looks like a non-interacting one except for the energies are now replaced by they have to resemble same minus sigma k omega as seen at this stage. This is exactly the form of the G0. Now, the energies are replaced by this xi k minus sigma k omega. Now, let us calculate h of which is a function of k explicitly. So, a sigma is written as, we are taking into account that same Fock term. So, this is a k minus q and omega minus omega, and this is a q omega. So, this is written as we have said earlier, when we discretize or rather use integral for q, then for a 3-dimensional integral we will write it at dq, and the normalization factor used over the first Brillouin zone is 2 pi whole cube, and there is a v q, and then there is a d omega over 2 pi, and then there is a g 0 and k minus q omega minus omega. So, it looks like that if we can calculate this integral, then we would be done in doing an infinite order perturbation theory, or rather we can get the Dyson equation or calculate the full Green's function and know what the self energy is. So, this is the expression for the self energy, and so this requires us to calculate integrals such as now, there is one thing that one should look at is that we are talking about really equal time Green's function, that is these two have the same times, which means that the frequency associated with it is infinitesimally small or going to 0, in which case we have the omega, small omega going to 0, then we have d omega by 2 pi and g 0 k minus q omega minus omega look like a simple minus n k minus q. This was once introduced while writing it, and then we had again written it as a Green's function. So, so this is that. So, as omega goes to 0, it will take the form of a number operator n k minus q. The reason is that this is d omega over 2 pi, and now this will be written as 1 divided by minus omega minus psi k minus q plus I eta k, and this is equal to I d omega by 2 pi. We put omega going to 0. So, limit omega going to 0, because these are equal time, it happens instantaneously, this interaction, and now we have minus omega minus xi k minus q plus I eta k, and the pole is at omega equal to minus k minus q minus I eta k. Now, it is always true that corresponding to a minus energy, there is also a plus energy. So, this, if it is true, then we have the pole at k minus q minus I eta k. Now, consider k minus q is greater than 0 and I eta k equal to I eta, then of course, it is taking the sign of the xi k. So, the pole at omega equal to psi k minus q minus I eta. So, now the pole is in the lower half. So, pole is not in the upper half. So, the integral is equal to 0. So, if you want to close it from top, now also, so pole is above the pole is in the below the real axis, so if the loop is enclosed in the upper half, then the integral is 0. Now, suppose psi k minus q is negative, in which case my I eta k equal to minus I eta. So, pole is equal to omega equal to psi k minus q plus I eta. One simple pole in the upper half plane and doing a contour integral. So, you have a d omega by 2 pi g 0 k minus q omega minus omega, it is equal to 2 pi I into sum of residues, 2 pi I into sum of residues, and the residue here is equal to 1, because it is equal to omega minus k minus q minus I eta divided by omega minus k minus q minus I eta, which is equal to 1. So, that gives the integral to be equal to the above integral to be equal to 2 pi I. Now, you multiply it with I over 2 pi. So, the required expression multiply with I over 2 pi, which was there here I over 2 pi. So, I over 2 pi, and then the whole thing becomes it gives you I by 2 pi into 2 pi I, which is equal to minus 1, and one gets a minus 1 into n k minus q. Okay. So, then you recognize that minus, so the sigma k omega becomes equal to a minus d q by 2 pi whole cube v q and n k minus q. I can, since q is being integrated over, I can use q as a dummy variable and redefine k minus q as q. So, q becomes k minus q. So, that becomes equal to d cube q by 2 pi whole cube, and I have a v k minus q n q n q, I am writing it. So, I can simply write this as because n q is a number operator which will have a value equal to 1 at t equal to 0, for q to be less than k f only, where n q will have a value equal to 1. So, I simply get a d cube by 2 pi whole cube and a 4 pi e square over k minus q square, and this integral if you perform, it becomes equal to e square k f over pi and 1 plus 1 plus 1 minus k over k f whole square divided by 2 k over k f and log of k f plus k and k f minus k. And so, this is at this level, it is independent of omega. So, omega means I should write it with the capital omega. So, it is it is simply so the at this level it simply renormalizes the bandwidth. There is an interesting cartoon on the perturbation theory that one can present. This is a book by Matuk, in which he gives an analogy between a propagator or a full Green's function and the drunken man. So, the drunken man, if you look at it carefully, though the resolution is not good, he started from 1, which is his original location, and then while going back home, home is at 2 here, he is undergoing repeated sort of deviations into various bars. So, these are Alice's bar, and then there are other bars which are written here. So, he goes and gets scattered by each one of them, and then he multiple times he goes and he comes out by as shown in the path, and then he goes here, and then he before he goes home he goes to a Dixie bar and all that. So, basically his full propagation is given by the full Green's function g, and he is outside the bar, the travel is given by the g 0, and then he could have gone. So, one option is that he could have gone directly from here to here, or he could have just visited one bar which is like 1 sigma, and so it could have been like this bar that he visits and then goes back home. But so, one is g 0 and then he scatters at the bar and then he goes back home, or he could do at 2 bars and and then finally goes back home. So, which means that he goes here and then he goes here and then he goes home and so on. So, his entire trajectory will be actually formed by taking the combinations of all these paths that he takes, and this full propagation would be described by a perturbation theory that we have presented here.